There is a 2-mile strip of water in Europe that seems designed to destroy anything humans put near it. The currents spin fast enough to swallow ships. The winds hit hurricane speeds. And beneath the surface, 2 tectonic plates are grinding together in one of the most active earthquake zones on the planet. For 2,000 years, this strait has been a graveyard for engineering dreams. But now, Italy has signed a $15.5 billion check to do the impossible. Build the longest suspension bridge in history, right over a geological time bomb. The question isn't just how they plan to build it. The question is, are they crazy for even trying? Between the toe of Italy's boot and the island of Sicily lies a stretch of water barely 2 miles wide. It looks innocent on a map, just a thin blue line separating 2 pieces of land. But the Strait of Messina is anything but innocent. This is where 2 seas collide. The Tyrrhenian crashes into the Ionian, creating currents so violent they spin into massive underwater vortexes. Ancient sailors called them Scylla and Charybdis, mythical monsters that dragged ships to their doom. The myth was wrong about the monsters. The danger, absolutely real. In 251 BC, Roman engineers watched their armies struggle to cross this strait during the Punic Wars. Thousands of soldiers, horses, siege equipment, all needing to reach Sicily. So they attempted something audacious, a floating bridge made of wine barrels and wooden platforms. Lashed together with rope and hope, it lasted exactly 1 storm. But the dream never died. For 2 millennia, emperors, kings, and modern politicians have stared across these waters and imagined a permanent connection. In 1870, engineers proposed a tunnel. In 1969, they drafted plans for a bridge. In 1981, they refined those plans. In 2001, they began preliminary construction. Every single attempt ended the same way: abandoned, defunded, politically killed. Until now, beneath the Strait of Messina runs one of the most active seismic zones in Europe. This isn't just earthquake country. This is where the African tectonic plate is literally diving beneath the Eurasian plate, grinding, slipping, building pressure that releases in catastrophic bursts. In 1908, a 7.1 magnitude earthquake struck Messina. The city was annihilated. Tsunamis swallowed the coastline. Over 80,000 people died in minutes. The ground didn't just shake, it liquefied, twisted, ripped apart. Now imagine building a bridge there. The design has to account for the towers moving independently during an earthquake. Not inches, feet. The deck needs to flex, absorb energy, and somehow not collapse when the ground beneath is literally tearing itself apart. Engineers have proposed seismic dampers, shock absorbers the size of buildings, foundations drilled so deep they reach bedrock untouched since the age of dinosaurs. The main span? 3,300 meters. That's over 2 miles of suspended roadway hanging from cables. To put that in perspective, California's Golden Gate Bridge spans 1,280 meters. Turkey's Çanakkale 1915 Bridge, currently the world's longest suspension span, reaches 2,023 meters. The Messina Bridge would shatter that record by over a kilometer. Why does distance matter? Physics. Every meter you add increases the load exponentially. The cables must be thicker. The towers must be taller. The forces trying to twist, bend, and rip the structure apart grow exponentially stronger. This isn't just scaling up existing technology. This is pushing into uncharted engineering territory. Wind speeds in the strait regularly hit 67 miles per hour. During winter storms, gusts exceed 90. These aren't gentle breezes. They're focused blasts, funneled through the narrow channel, accelerated by the surrounding mountains into a natural wind tunnel. Engineers learned this lesson the hard way in 1940 when Washington's Tacoma Narrows Bridge twisted itself to death in 42 mph winds. The footage is haunting, some massive steel structure undulating like a ribbon before tearing apart and collapsing into the water below. The Messina design incorporates a revolutionary deck structure, partially open, designed to let wind pass through rather than push against solid surface. Wind tunnel tests have been run thousands of times. Computer simulations model every possible storm scenario. But here's the truth. Until it's built, until it faces a real Mediterranean tempest, no one truly knows if it will hold. Remember Scylla and Charybdis? Those legends came from somewhere real. The strait's currents reach speeds of 7 knots, fast enough to spin ships off course, create massive whirlpools, and make the water churn like a washing machine on full power. These currents change direction 4 times a day, driven by tidal shifts between 2 different seas. Building bridge foundations in these conditions means working in water that actively fights you. Every concrete pour, every pile driven into the seabed, every underwater weld must be timed perfectly between current shifts. Construction vessels will need dynamic positioning systems, essentially hovering in place against forces that have swallowed ships for 3,000 years. The Strait of Messina isn't just water, it's one of the Mediterranean's most critical ecological corridors. Whales migrate through here. Endangered fish species spawn in these currents. Seabirds nest on the cliffs. Environmental impact assessments have stretched across thousands of pages. Marine biologists warn that construction could disrupt migration patterns permanently. Vibrations from pile driving might drive cetaceans from critical feeding grounds. The bridge's shadow, yes, the literal shadow, could alter water temperatures enough to affect plankton blooms that feed the entire marine ecosystem. Then there's the land. Ancient groves of olive trees, some over 500 years old, sit directly in the path of access roads. Archaeological sites dating to Greek colonization could be destroyed. Local fishing communities that have worked these waters for generations face an uncertain future. The question isn't whether the bridge will cause environmental damage. The question is whether the damage is acceptable for what Italy hopes to gain. If they build it, and that's still an enormous if, the Strait of Messina Bridge will be unlike anything humanity has ever constructed. Picture 2 structures, each rising 382 meters from their foundations, taller than the Empire State Building, taller than most skyscrapers you've ever seen. These aren't buildings, they're bridge towers, designed to support weight measured in hundreds of thousands of tons. The foundations will be drilled 120 meters deep, anchored into solid rock through layers of sediment, soil, and seismic instability. Each tower will contain enough steel to build 30 Eiffel Towers, enough concrete to construct a dam. 2 main cables, each over 5 feet in diameter, will arc across the strait. Inside each cable, over 44,000 individual steel wires, bundled, wrapped, and tensioned to hold the entire structure aloft. If you laid those wires end to end, they'd stretch from Rome to New York twice. A 6-lane roadway plus 2 railway tracks, all suspended in midair. The deck will be designed with a unique aerodynamic profile, shaped like an airplane wing to manage wind forces. Sections will be assembled on shore, then floated into position and lifted by crane in a choreographed dance of precision engineering. And it all has to move. During an earthquake, the towers might sway several meters in opposite directions. The deck must flex, absorb that motion, and somehow not tear itself apart. Engineers call it controlled failure, designing a structure that bends without breaking, that survives by moving rather than resisting. Every meter of cable will have embedded sensors, monitoring tension, corrosion, stress. Artificial intelligence systems will analyze, Data in real time, predicting maintenance needs before failures occur. The bridge will essentially diagnose itself, a living structure constantly monitoring its own health. This isn't just a bridge, it's a proof of concept, a declaration that human engineering has reached a new level of ambition and capability. So here we are, the plans are approved, the budget is allocated. Italy's government has promised 120,000 construction jobs. Economic studies predict $5 billion in annual benefits from improved Sicily mainland connectivity. But we've been here before. In 2001, Prime Minister Silvio Berlusconi laid the ceremonial foundation stone. Construction contracts were signed. Workers mobilized. Then 2006 arrived. A new government took power, and the entire project was canceled. The foundation stone? Still there, a monument to political promises, turned to dust. The current government has set a completion date, 2033, 8 years to design, finance, and construct one of the most complex engineering projects in history, in a seismically active zone, during a period of economic uncertainty, with environmental lawsuits already being prepared. The skeptics say it's political theater, a grand gesture that will quietly die when the headlines fade and the true costs become clear. They point to Italy's infrastructure history, to the half-finished highways, the delayed rail projects, the chronic inability to complete megaprojects on time or on budget. The optimists say this time is different. New EU funding mechanisms, Chinese engineering firms interested in partnering, a post-pandemic push for infrastructure investment, climate goals that demand better rail connectivity to reduce air travel. But let's talk about what $15.5 billion actually means. That's more than Portugal's entire annual infrastructure budget. It's enough money to build 15,000 schools. It's 30 times what Italy spends annually on earthquake preparedness. Is connecting Sicily worth that price? Economically, maybe. Symbolically, absolutely. But practically? The truth is, we won't know until 2033 if the bridge exists. If it doesn't, this will become another chapter in humanity's greatest engineering dream. Another almost. Another 2,000-year-old idea that physics, politics, and reality conspired to keep impossible. The Romans tried with floating boats. We're trying with steel cables and AI sensors. The strait hasn't changed. Still dangerous, still unforgiving, still waiting to test whether human ambition can finally overcome nature's most perfect barrier. In 8 years, we'll know if the dream finally became real. Or if Scylla and Charybdis claimed one more victim, not a ship this time, but a $15.5 billion bridge that existed only on paper. The countdown has started. The question remains, will they actually build it?